Introduction to Itanium processor. What is Itanium processor? Itanium is Intel's first microprocessor based on 64-bit architecture. It is commonly used in high-end workstation and enterprise servers. The underlying architecture of Itanium is called IA64. The Itanium architecture originated at Hewlett-Packard (HP) and was later jointly developed by HP and Intel. Intel initially marketed the processor for enterprise servers and high-performance computing system. Itanium access to very large memory (VLM). Itanium also made use of clever compiler to enhance the way commands are delivered to the processor. Processing time was significantly lowered, which improved the chip performance. In contrast to 32-bit microprocessors, which require the information to be decoded before being used by the 64-bit processor, Itanium can handle 2 out of 3 sets of data without the need for additional clock cycles. Large-scale applications that require more than 4 GB of RAM, such as web servers, database, enterprise source planning (ERP), high-end operating system, and internet router are frequently powered by Itanium.
The architecture of Intel Itanium. The Intel Itanium architecture, also known as IA64 or Intel Architecture 64-bit, was developed by Intel in collaboration with HP. It was primarily designed for high-performance computing and enterprise-level server systems. The Itanium architecture is based on explicit instruction-level parallelism, in which the compiler decides which instruction to execute in parallel. This contrasts with superscalar architectures, which depends on the processor to manage instruction dependencies at runtime. General architecture of Itanium can be summarized by 9, which is instruction, fetch and decode, instruction queue, instruction scheduler, execution units, predication, register stack, memory hierarchy, coherency mechanism, and lastly is system interface. The IA64 architecture was designed to overcome the performance limitation of traditional architectures and provide maximum headroom for the future. To achieve this, IA64 has an array of features to extract data ILP, including speculation, prediction, large register file and register stack, advanced branch architecture, and many others.
We proceed to the register organization. The architecture and organization of this processor divide the register into 5 main groups. First, general purpose registers, which typically had 128 registers. Second, predicate registers, which had 64 registers that were used to control the executions of instructions based on certain conditions. Third, branch registers, which had 8 registers that used to store target addresses for branch instructions. Lastly, we have floating point registers, which had 128 registers for computation and storing arithmetic data. Then we proceed to memory organization. The Itanium architecture supports a large virtual and physical address space for efficient memory access and management. Firstly, Itanium processor supports a 64-bit virtual address space, allowing for a vast range of addressable memory locations. Second, the physical address space in Itanium processors also supports 64 bits. The processor translates virtual addresses to physical addresses using page tables and memory management techniques. Then we proceed to the cache organization. The cache organization of Itanium processors typically included 3 levels of cache: L1, L2, and L3. The L1 caches are typically small and located closest to the processor cores for low latency access. The L2 caches are secondary cache that are shared among all processor cores in a multi-core Itanium processor. The L3 cache can store a larger amount of data, enabling improved data sharing and reducing memory access latency. We proceed to the system bus of the processor. The system bus facilitates communication and data transfer between the Itanium processor and various system devices. First, front size bus FSB, which is the primary bus that connects the Itanium processor to the other system components. Second, we have the Itanium processor family introduced the scalable coherent interface, which is a high-speed point-to-point bus used to connect multiple Itanium processors within a multi-processor system, which enabling the parallel processing and scalability. Then we have the system bus connects the Itanium processors to the memory subsystem, including system memory modules such as DRAM. Lastly, we have input-output module or interfaces that enables data transfer between the processor and peripheral devices.
Okay, now I will proceed about the data transfer between processor and peripheral in Itanium, Intel Itanium. So the main use in this data transfer is direct memory access. The function of DMA allows the processor to transfer data directly to and from the memory without involving the CPU. This helps to free up the CPU time and resources, making data transfer more efficient. About the peripheral device, when we want to transfer data from the processor to the peripheral, the processor uses DMA to send the data directly from the memory to the peripheral devices. So how the processor send the data? Well, it uses something called an input-output address. An I/O address is like a special code that tells the processor where the peripheral is located in the computer system. When the processor knows the I/O address, the data travels through the special channel called buses, which act like highway for the data transfer. These buses connect the processor, memory, and peripheral together, allowing them to communicate with each other. During the data transfer, the processor and the peripheral devices work together as a team. They exchange signal and follow a set of rules to ensure the data transfer is transferred accurately and efficiently. Next, I will explain about the ALU structure. ALU structure is to perform arithmetic and logic operation. It's like a little brain inside the processor that helps it solve math problem and make logical decision. Centrifugal branch and predicate is to help the processor make decision and perform a task. Want to add integer in register is to hold data and perform calculation in small storage. And lastly, want to add floating points register is to hold floating point, which are numbers with decimal point or fraction. That's all for me. Thank you.
Instruction decode Intel Itanium. In the Itanium architecture, the instruction decode stage is a crucial part of the processor pipeline. It involves decoding the instruction within a fetch bundle to determine their type, operand, and any dependencies or constraints associated with them. It is designed to sustain the execution of 6 instructions per cycle, although it has enough issue control and data path to issue 9 instructions per cycle. Here is a instruction type and execution unit type. Each IA64 instruction is categorized into one of 6 types. Each instruction type may be executed one or more execution unit types. Extended instructions are used for long immediate integer and long branch instruction. 3 instructions are grouped together into a 1 to 8 bit container called bundle. Each bundle contains 3 41-bit instruction slots and a 5-bit template field. There is 12 template types. Each letter in a template type represents the mapping of instruction to execution unit. Each instruction must be placed in slots corresponding to their instruction types. based on the template specification, except for a type instruction that can go into either I or M slots.
Hello, Assalamualaikum. My name is Haziq Naufal, and now I will explain about Itanium microprocessor pipeline. The cycle time and the core pipeline are balanced and optimized for the sequential execution in integer scala codes. By minimizing the latency of the most frequent operation, thus reducing that time in the overall computation. And then the cycle time of accommodates the following key critical path is single cycle ALU, which is globally bypassed across 4 ALUs and 2 loads, and then 2 cycles of latency for load data returned from a dual ported level 1 cache of 16 kilobytes. Lastly is scoreboard and dependency control. Okay, this is the figure illustrate the 10-stage core pipeline. They has 4 function core, which is front end, execution core, operand delivery, and then instruction delivery. The explanation about 10-stage core pipeline is the bold line in the middle of the core pipeline indicates a point of decoupling in the pipeline. The pipeline accommodates the decoupling buffer in ROT, which is instruction rotation stage. The pipeline also dedicates register remapping hardware in the REN, which is register rename stage. The pipeline also access the large register file across WLD, which is words line code, and REG, which is register read stage. And lastly, the DET exception detection, which is accommodates delay branch execution as well as execution management and speculation support. Proceed to the application of the microprocessor. Itanium is widely used for driving large-scale applications that run more than 4 GB of RAM memory, which is web server. Secondly, enterprise resource planning, which is ERP, and then database, and then high-end operation system. Lastly, internet router.
In conclusion, the Itanium processor was a high-performance microprocessor developed by Intel and HP. It includes a distinctive architecture known as EPIC, explicitly parallel instruction computing, which places a focus on parallel processing. It makes use of a cache hierarchy and provides a sizable memory address area to minimize memory latency. The Itanium processor's ALU, arithmetic logic unit, carried out arithmetic and logical operation, and it had a specialized instruction cycle for carrying out commands. For the purpose of transferring data between the processor and peripherals, a bus system was used. The Itanium CPU, however, had issues because of its instruction set architecture (ISA) and constrained program compatibility. The demands for Itanium-based system declined as a result of the 89 architecture supremacy and improvement in mainstream processors.